Hello everyone. Today we're going to be learning a lot about different types of errors. Now, the reason errors are important are because when we're making calculations or more specifically if computers are making calculations, they're going to have to make important rounding or chopping or truncation decisions of I only have so much precision, how much can I allocate for this specific number before it has to just cut it off and then just save what it has. So with that being said, we have a lot to go through, so let's just start at it. So now our first type of error are round off errors. Now essentially round off errors, they occur because computers have finite precision. So that'd be when storing numbers. So now, with this, there are actually two different types of round off errors. So we have two types. The first one is chopping. And now with chopping, essentially what that is let's say we have some constant c that is equal to 4.9867321. And what we're going to do is we're going to chop off all of the digits after the third decimal place. So we'll essentially draw our line here and we'll essentially chop off all of those digits. So then C would then be equal to 4.986. And now because of this, notice that our final value is different from the original. So this will actually lead to some error because it's not the same as what it's supposed to be. So now with this, we tend to denote the rounding error as e to the r. So we'll essentially say the absolute value of our rounding error is going to be equal to our original number, or the 4.9867321, subtracted by what our essentially approximated value is, which in this case would be 4.986. And then that's pretty much chopping. Now, the second type of our rounding error is rounding itself, or the round off error. So essentially, with that same constant, so let's write that out here. Let's say we were to round after the third decimal place. So we'll draw this line again just to denote it. And we can say this 6 here, it's at the p position. And we can say the 7 here is at the p plus 1 position. Now, one thing I should probably note is if our p plus 1 position is greater than or equal to 5, then what we'll do is we'll increment our p by 1, or we'll essentially add 1 to the p value. So essentially like normal rounding, pretty much. Because in this case, since 7 is greater than or equal to 5, we'll round up our c, so that's 4.987. And now we calculate the error for this by doing essentially absolute value of e to the r, where r represents round off error. And that will be equal to the original number, or the 4.9867321, minus the 4.987. So now we hit basically our first type of error, which is our round off error. Now the second type is going to be the truncation error. So now the truncation error occurs when a computer is forced to approximate a procedure with infinite operations. So I'm going to write that out real quick. So it occurs when a computer's forced to approximate a procedure with infinite operations. So, for example, let's say we had sine of x and we did the Taylor expansion for it, which is equal to x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial, and then on and on and on, because this will essentially have an infinite number of terms. So what if we were to say, let's use one term to make an approximation. So let's say we want to approximate pi over 6 for sine. So then we'd have sine of pi over 6, which is going to be approximately equal to pi over 6, which we can say that'll be equal to 0.52395, and then dot, 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 because it's going to be a irrational number. Now, we know from our trigonometry that sine of pi over 6, its true value is going to be 1/2, or 0.5. So we can tell that this 0.52395 dot, 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 there is some error with this inherently because it's not accurate. Like it's not our actual true value. So we can say that our error truncation, so the TR stands for truncation, that's going to be equal to the true value, which is 0.5, minus our approximated value, or 0.52395 dot, dot, dot. So that'll give us about negative 0.02395, on and on and on. So now let's say we were to use two terms. So say let's use two terms. Now what do you expect will happen if we were to use two terms? Well, what should happen is we should get a more and more accurate answer with a smaller and smaller truncation error as we increase our number of terms. So we can say that sine of pi over 6 will be approximated as pi over 6 minus, say, pi over 6 cubed divided by 3 factorial. And that'll give us about 0.4996742 dot, dot, dot. So then our truncation error, say e to the tr, that will then be equal to our true value, 0.5, minus 0.4996742 dot, dot, dot. So that'll actually equal 0.0003258. So that's already a good bit better because we have a lot less error than the first one. So now we actually know how to essentially express our error using truncation, and we know how to express our error using round-off errors. So now the third type of error that we have is the true error. Now with the true error, there are actually two different parts to this because we have the true error and we have the total error. Now the total error, let's do that one first. So we'll say total error. That is going to be equal to our rounding error plus our truncation error. And then with our true error, that is going to be equal to our true solution, or our true value, subtracted by our numeric solution, or our numeric value. So essentially what this means is for our total error, we're taking our e to the r. Now this will have to be for the same problem because these are both two different problems. So obviously we can't intermix these two errors. But if we did have one problem, then what we would do is we would essentially take our rounding error, and then we'd add that to our truncation error, and then that would equal our total error. Now for our true error, we can actually do a quick example of this. So if we say example, so let's say we have a wood board with a true length of 48 inches. And we can say, but a tape measurer measures it to be 47.94 inches. Then what we'd say is our true error is going to be equal to 48 minus 47.94, which will leave us with 0.06 inches. So that's essentially our true error for this example. Now, going into the next type of error, it actually kind of builds off of our true error, because this is our true relative error. So now with the true relative error, this is actually expressed, so we'll say true relative error is going to be equal to our true solution minus the numeric solution, and this is all going to be divided by the true solution. So this will actually give us some sort of decimal point number. And then building off of this, we can say that the percent error is equal to the true relative error times 100% to then put that into some sort of percentage value. So let's build off of this wood board problem here and do a extension example. So we'll say using the board example, what is the percent error? Well, to calculate that, what we would do is we could say percent error is going to be equal to our true solution, which we said was 48 inches, minus the numeric, which was 47.94 inches, divided by the true, which is 48 inches, and then we'll multiply this by 100%. And this comes out to be 0.125%. And so that is yet another type of error. Now, to round this off, we have two more types. The next one up is our proxy error. Now, for the proxy error, this would apply to, you could say, different approximation functions. So, for example, if you're trying to find the x-intercept of some sort of function, you could actually use the proxy error to determine what the error is between your current value that you're approximating versus the previous value that you're approximating. So let's write this out. So we can say for a given value x subscript k, its proxy error is going to be equal to the absolute value of x sub k minus x sub k minus 1. So this essentially says if you had some value of x, let's say 5, and its previous value, x sub k minus 1 was 4, you'd essentially take your difference and then take the absolute value. So then the proxy error would be 1, which that's a very bad error. But as you get more and more precise, let's say, again, going back to our example of an x-intercept, you want to try to get that closer and closer and closer to your actual x value, where your essentially function is equivalent to 0. So that'll get closer and closer, and then your proxy error will get smaller and smaller, ideally, if it's a good approximation. So that's essentially proxy error. Now, for the last type of error that we will talk about is the residual error. So we'll move that up here. And now for the residual error, we can say for a given value, again, x sub k, its residual error is going to be equal to the absolute value of f of x sub k. And then that's pretty much it. So essentially what this means is, let's say you're, again, going back to the example where you have some sort of function, f, and you're trying to find its x-intercept. You can see as we get closer and closer to that x value, what will essentially happen, ideally, is that your function will get closer and closer to 0, which that'll be your residual error above or below 0, because you want to try to hone in and get your function as close to 0 as possible before you say, yes, this is the x value that is indeed corresponding to our x-intercept. So I know that was a lot of different types of error, so feel free to go back through the content, kind of walk through some of the examples, and then just try to differentiate them. So I know it seems like a lot at first, but the more you use it, I promise it will certainly catch on. You'll get the hang of it in no time.